Welcome guys. So in this video, after we finish vector space, some basic linear algebra, then we are starting to talking about some interesting stuff. So this is the introduction of module. Okay. Yeah, so module is basically like generalization of the abelian group. Okay, so we will start to see. Okay, so definition. So they are be any ring. So R can be any ring. So usually we talk about commutative ring with identity, but not restricted to such example. Okay, and then you have a non-empty set. Let's call it M. It's called R module. Is called R module. If the following is true, so basically you need to give it the result, give it the criteria. So you need to have a non-empty set M is called R module. Okay. So the first is that M need to be abelian group, right? So you're pairing, so you have a ring and abelian group. Okay, and the second is that there is a map, basically R apply M to M. So basically what I'm saying is that you should view R as a coefficient and act on M, right? So the Rm is well defined in M. So if you choose R to be filled, then this is just a vector space, right? So okay, so and satisfied. 3. The first one is RA plus B is RA plus RB, and RSA is basically RSA, and also R plus SA equals RA plus SA. So RS are basically all the ring, and yeah, A is just the module A. Yeah, so some language. So if one say that the unito module, so unito module means that the ring is assumed to be have one identity, and also one M must equals to M for all M belongs to M. Okay. Okay, and so in this video we focus on the unito module, and basically our ring must have the commutative. It must be commutative with the identity. So actually, this definition is basically referred to a left R module. Okay, so once you have this property, then I would say M is a left R module. Okay. So example. The example, the first is the any group, right? So group is basically Z module. Okay, this is obviously right because in the group, G group should be abelian group, right? So given abelian group G, right? So you can natural Z act on G will be if XG just G X times. Okay, and easily see satisfy all this property because SA means A go S time and the go R time is the same as RSA, and trivial, and this is also trivial, right? Because you go S time, go R times, basically it's R plus S times. Okay. Also, so given any commutative ring itself is also R module, right? So R is also R module, and then not just this. If you take any ideal, let's say lambda, and you can quotient lambda, right? So R quotient lambda is also R module. Okay. Yeah, R quotient lambda is also R module. Okay, right? So the operation basically take R, and then the form R module lambda will be x plus lambda, right? So R times x plus lambda defined to be Rx plus lambda. Yeah, and also the addition I already told you just the ring, the definition of the quotient ring, right? So the addition x plus lambda plus y plus lambda equals to x plus y plus lambda. Okay, and definition, and the called submodule. Okay, so submodule is I think it's easy, right? Because if M1 is a subset of M, which that R will the closure is correct, means that if you forget about M, then the M1 is also R module. by the same reason. So this is called the submodule. Okay. Okay, so let me talk about direct sum. So this is the important part, direct sum. Okay, so in a vector space, I mean, the direct sum is somehow easy, right? In a vector space, if you write V is a direct sum of V1, V2, direct sum up to Vn. So what you are saying is that given any V, there is a unique way to write as V1 plus V2 up to Vn, right? So this is the direct sum in linear algebra, or basically in the vector space. So vector space is special module, right? If you work in the field. Okay, but I want to talk about the direct sum. So the direct sum in the modules language means that if M is a M1 direct sum M2, there is a Mn, right? So if I write it this way, then I should first notice that the definition should says that Mi is a submodule of M, right, for each I. And then not only that, yeah, by the way, this is unique. So the same definition says that for every M belongs to M, then there's a unique way. So this unique is very important, unique way such that M is equals to M1 plus M2 up to M. Okay. Yeah, this is the same, that's almost the same definition, right? In the direct sum of modules. Okay, so let me, so also now a definition called cyclic module. Okay. Okay, so if I say M is a cyclic module of R, so if M is a cyclic R module, means that so it means that this M is basically R. There exists, so I should say there exists A belongs to M, such that all the M is somehow like a permutation of ring. You use a ring to do a permutation, so it's RA belongs to M. So all the M comes from R times A. A belongs to M. So if it looks like this form, basically called the cyclic module, or basically somehow people sloppy, I write A parentheses. Yeah. Okay. So let's talk about another definition called the finitely generated. Okay, so when I say M is finitely generated R module, if what? I mean, if you can find A1, A2 up to AN in M, so you can find an element in N such like as a basis, look like basis, right? But not the same. Such that every M, right? So you pick up something, you pick up M, right? Such that this M is equals to, let's say, R1A1 plus R2A2 up to RNA. Oh, it's a little bit. Yeah. So yeah. Basically, sorry, that's stupid. Okay, so what I'm saying is that given M, so you fix this. It looks like the basis, and every N is a linear combination of this A1, A2 up to AN. So use R to do the permutation. So in the vector space, that this is just a finite dimension, right? And if there are linear dependent, then you will say this is basis. Okay. The problem is that in the ring is not in the module is not obvious. Okay. Okay. So the important theorem that this video want to prove is the following. So actually we prove the weak version. So let R be the Euclidean ring. Okay. So basically, in our proof, I only prove the integer, right? But I will talking about how to prove generally. If we prove integer, then it's already very close. So if you work in a Euclidean ring, then every finitely generated R module is a direct sum of cyclic module. Okay, so what I'm saying is that if R is a Euclidean ring with integer, then this module M, you take a finitely generated R module, is basically the direct sum of the cyclic. So you can write it as this. and each of these is just cyclic. And so basically, you can find some element in the basically it's cyclic submodule, cyclic submodules. Okay, so what I'm saying is that you can find M in the M1, and M element like A0, A1, there is some A2, up to the AN. Okay. Okay. Yeah. So this theorem is not so trivial. Okay. So some people may say that this is trivial, but the actual is not. Okay. Yeah. So let me just let's see the idea. So the idea is suppose M is a finitely generated module, right? So it's finitely generated, so that means that then you would say that each let's say each x belongs to M, then you can write as let's say R1, R2, A2 up to Rn, An, right? For some all these belongs to M, right? So this is X. Okay. Okay. But the problem is, so theorem says that so you can find some B, so you can find some others. You find some others like let's say B1 up to BQ, right? Such that this any X belongs to M can be uniquely written as the linear combination of it, right? So X can be written as uniquely, let's say as B1 up to SQ BQ, right? All these SI belongs to ring. Okay. So the problem is that the theorem, the difficult part for theorem is this unique. Okay, it's not guaranteed. So you only guarantee that in this abstract sense that you can write this x into a linear combination of all these A1, A2, An because it's finally generated by this theorem do not have this. But this do not immediately tell you that you can find some others, right? Such that this X can always uniquely written as this. So the difficult part is that the theorem, this uniqueness, actually need to based on a ring structure such that you choose your ring to be Euclidean ring. Okay, so let me just remark. So actually, this remark will just tell you that. Actually, you can weaken these results to change this ring to be just a principal ideal domain. Okay, but what I'm saying is that so this proof is not just the module itself. You need to use the R module, which you need to somehow come up with some idea to use the property of this Euclidean ring. So once you use the Euclidean ring, then you have the chance to prove this such a theorem. Okay, it's not difficult. It's not so difficult, but it's not trivial. Okay. Okay, so let me talk about what's uniquely mean. Okay. So I say that if you can write, this one, right? So I'm not saying that this S1 up to SQ are unique. So I'm saying that if one can write this S1 into another, so another, let's say this one. Okay, so I'm not saying that this S1 is the same as this S1 prime. The unique means that but I can conclude the S1 B1 will the same as S1 prime 1 B1. Okay, but you might think that this must same, they are the same, right? But no, right? Because we are working in the module, right? We are not working in the field, so you cannot delete B1, and we are not in the vector space. So even though you can say B1 is not non-zero, but you cannot delete them. Okay, so we are not working in a vector space. So don't be fooled. Okay, so proof. So in order to prove, let's change the Euclidean ring to be the general integer. So we only prove the integer case, but we just modify a little bit and then we prove the Euclidean case. Okay, so proof is induction. Okay, so the induction means I working in a rank of the M. So the rank of module means that since M is finally generated, right? So I can tell that I can define the rank to be the minimum generating set. Okay, so the minimum element I need to generate in M. Okay, so the first case that rank M is 1, right? I mean, if the rank M is 1, then M is already just can be generated by some single element. So let's say A. Okay, by definition, M is a signaling module. So proof is done. Okay. Okay, so let's say, and then we say that theorem. So we say that theorem. So we assume that theorem works for rank. Let's say the rank M is Q. And then we say that theorem works for rank Q minus 1. Okay. Okay. So now the key point is that we start to prove, right? We start to prove. Okay, so we get the minimum generating. Suppose we get some minimum generating set, such as A1 up to AQ. Okay. So once we get this, and let's see. Okay, so let's say if we have a relation such that N1 A1 up to NQ AQ 0. So this is a relation. So suppose we get some relation like this, and this implies, suppose this implies that N1 A1 equals to N2 A2. By the way, this N1 to NQ are just some integer. Equals to NQ AQ 0. Okay, so by the way, these are all assumptions. So I'm just do some investigation. So if we have these results, and suppose this will imply this, then what? Then obviously this is unique, right? So obviously prove that M is a direct sum. M is just direct sum, right? Because this means that this is unique, right? Because if I get two of them, then I will get this one the same as this one. Okay, right? Okay, so the reason is that, I mean, you can write it as S1 minus S1 prime, B1 S2 minus S2 prime B2, right? So SQ minus Q prime BQ, right? And by your assumption, if any relation give you this, and you can imply that the coefficient will be the same, you can imply that this guy will be 0, then definitely you will have this. Okay, so this will imply that M is direct sum of A1, A2 up to AQ, right? So basically you're done, right? Because each MI just a signaling module. Let me just rephrase the idea. So what I originally say is that so the idea is that if let's say if okay, so this is an ideal case, right? So in the ideal case is that if N1 A1 plus N2 A2 up to NQ AQ 0, if this will implies, so this is if this will implies that N1 A1 0, N2 A2 0, and all of it 0, so NQ AQ 0, then we will show that M is just the direct sum of A1 A2, right, up to AQ, right? So in this ideal case, then everything is easy. Okay, so what I'm saying is that so idea is that if this is not true, then we should be able to come up with another linear combination such that this is true. Okay, so what I'm saying should be this, right? So let's see, if I given a minimum generating set, minimum generating set of M. Let's say this is A1, A2 up to AQ. Okay, and what, right? And then let's say if you give me any generating set, and I ask whether this property happens. So what I'm saying is that I collect set called omega. Okay, so this omega is the let's see, it's the all the coefficient such that let's see, so such that let's call it S1, S2 up to SQ, such that S1 A1, S2 A2 up to SQ AQ 0, but do not implies S1 A1, S2 A2, S3A3, SQAQ is 0. Okay, so this is the most difficult part in this proof. So given any, so what I'm saying is that, by the way, and this A1, AQ are minimum generating. So for M, right, I can create various minimum generating set. So I can create a lot of generating set. Okay, and then for each generating set, I can collect such coefficient, which that this property fails. And among all the generating set, I pick an element. Such that it's omega, such that it's the minimum of this coefficient. Okay, so yeah, I mean, okay, so this is the most difficult part. Okay, so what I'm saying is omega is the among all the coefficients, among all the minimum generating set, such that this property fails, and I collect all coefficient. I collect all the coefficient, and I pick the smallest one. Let's say this is S1. So pick the smallest one. Okay, so this is the most abstract part. Okay, so let's see. Okay, so let's say this is, so remember this is integer, right? So let's say this integer is S1, and then let's see what happens. Okay, so let's see what happens. Okay, so right, so I define this integer as S1. So such that suppose we get some property this. Okay, and so this is the so among this S1, right? So S1 is the smallest for this property. So for this property do not hold. So we will get some equation which is like this, right? Particular for this S1, and I claim for other relations such as R1A1, R2A2, up to R2AQ equals to 0, which I claim that in this case that R1 must S1 must divide R1. Okay, and the proof is simple. I suppose not. But suppose not, then I can write R1 as, I can divide R1 by S1, right? So I get R1 is MS1T1T, right? So if I times M1 and use this minus this, then I get TA1 plus A2, AQ is 0, right? But the problem is that I already claimed that S1 is the smallest, right? But by the division, this T will less than S1. So the only choice is that T must be 0. So which that I prove this case. Okay, so this should be used as the lemma 1. Okay, so the lemma 1 says that any other relations satisfy this property must have S1 divides R1. Okay. Okay, so next. So next says that if S1, so now I go back to this relation. Okay, and I claim what? I claim S1 divides S2. Okay, and same reason, right? Suppose not. That means I can use S2 to divide S1, right? So for example, I can write S2 to be M2 S1 plus T. Okay, and if not divides, then T should be less than S1, right? So if this is the case, then I can write this equation as S1A1 plus M2 S1A2 plus TA2, right? SQAQ 0. Okay, right? But what? But if I define A1, so I can define, if I define A1 prime, so I can define A1 prime, right? Such that, so let's write as A1 plus M sorry. Okay, so I can define another. I can pull out this S1. So I write S1 A1 M2 A2 plus T A2 up to SQ AQ is 0, right? So let me define this to be A1 prime. Okay, so but now you get another minimum generating set called A1 prime A2 up to AQ, right? So in this relation, such that in this case that T, right? T is still smaller than S1, which is a contradiction, right? So T should be 0. Okay, so now you guys know a trick, right? Remember that omega is among all the minimum generating sets. I pick out all the relations such that this relation fails, and I pick the smallest coefficient, and I call it S1. Okay, so this is the most difficult part. By the way, this omega is just a subset. So each coefficient is a subset of the positive integer. So there's always a smallest one. Okay, so from this, you prove that you not just prove S1 divides S2, right? You can use the same reason. So S5 divides all S3 S up to SQ. Okay, so now consider the element called A1 prime, A1 star, such that A1 is M2 A2 up to MQ AQ, right? And consider AQ AQ. So easy to see that these all still generates M. Okay. I mean, you can check by yourself because by definition, this A1 should not be written as the linear combination of the rest. Right? Okay, so they not only generating M, right, and then they also have a strange property such that right, by definition, your S1 A1 star, if you times you get S1 A1 plus S2 M2 up to S. So by the way, this S2 is M2 S1. And the SQ is MQ SQ, right? Sorry, MQ S1. Okay, so this tells so S1 times A1 star will be S1 A1 plus S2 A2 up to SQ AQ, which is 0, right? Okay, nice. Okay, so now we can finish the proof. Okay, so let's see. So suppose you get R1's A1 star, so R2 A2 up to RQ AQ, which is 0, right? So this is supposed to come up with such relations, right? So if you use A1 star, A2, and AQ as your generating set for M, and you get something like this, right? Then by definition, then by the previous lemma, that R1, the S1 is a product of R1, right? But the problem is that S1 A1 star is 0. Okay, so this immediately implies that R1 A1 star is 0. Okay, so which show that suppose you get that M1 to be the cyclic module generated by the A1 star, and the M2 be another module such that A2 A3 AQ, and then you prove that the M1 intersection M2 is 0, right? Because there's no any elements live in the M1 inside M2, right? Because if there is this, then you will have this property, you will have this equation, but by previous lemma that it must be 0. And but obviously that any M, right, is basically the whole module M is just M1 plus M2. Okay. So I think this is trivial, right? By definition, this M, because they still generated M, right? So M is still the same as M1 plus M2 because it's always the A1 star and the A2 up to AQ. Okay, so that means M is direct sum of M1, there is sum of M2, and this M1 is what is generated by A1 stars, right? So this is a cyclic module. And for this one is rank M2 is Q minus 1, right? So by the previous induction, then I know this is a direct sum of cyclic module, so total M is a cyclic module. Okay, we finish a proof. So difficult. Calorie. So I only talk about 1 calorie. The next calorie, the Jordan Fong I leave in the next video. Okay, so simple calorie. So we know that if G is finite, G is a finite group. finite abelian group, right? And by definition, G is a Z module, right? With a finitely generated Z module because all G only has a finite element, so it must be finitely generated. So by it must the direction of cyclic module, right? And then what is a cyclic module? So cyclic module means that it's generated by a single element. So in the group theory language, this is called a cyclic group. Okay, so how we prove in the every finite abelian group is the direct sum of the cyclic group. Okay. Notice that Z is a Euclidean domain. Okay. So what is the general proof of the Euclidean domain? So remember that in the previous proof that I only working in I use the integer, right? But the proof is simple, right? Because I can just replace all the t less than s, like changing to dt less than ds. Okay, then that's done. You just change, you just use, because we only use the partial greater or equal to 0, right? But in a Euclidean domain, you can define this type of d. Okay. Yeah, so basically you can prove these results. Yeah. Okay, in the next video we will talk about applications. So applications on linear algebra. So what I trying to prove is that every complex finite dimensional matrix, or basically finite dimensional, it's n by matrices, can be written as a direct sum of the block form of Jordan, block diagonalization or normalization of Jordan form. Okay, so this is the famous theory in the linear algebra. So what I'm saying is that every matrix, right, can be written as the finite the block diagonal form, and each one is a Jordan form. Okay, so this is the final heart of linear algebra, but in the abstract algebra, just this theory. Okay, so see you guys in the next videos. Bye bye.